So this lesson is section 6.1, the indefinite integral. We're going to be looking at the definition of what an antiderivative is, and then the beginning rules of integration. So basically the rules that would allow us to find integrals. So up to now in our class, we've developed rules for differentiation and used the derivative for different applications, right? We've use the power rule, product rule, quotient rule, chain rule in order to find the derivative of a given function. And we've studied the graphs of the derivatives and then some applications. So we've looked at related rates type problems and applied optimization problems. Now we want to consider reversing that process. So when we've been finding the derivative of a function, we've said we've been differentiating. So in other words, we want to now anti-differentiate. In some situations, the derivative is known, and it can be helpful for us to find the function or functions with that derivative, or those functions being the antiderivative. So kind of just think of, we're going in the reverse now. You're given the derivative and you're finding almost like the original function. So if capital F and lowercase f are two functions and the derivative of capital F of x is equal to lowercase f of x for all x in the domain of lowercase f, then capital F is an antiderivative of lowercase f. So we could say capital F of x is the antiderivative of lowercase f of x. Now, antiderivatives differ by a constant. So if capital G and capital F are both antiderivatives of the same function, lowercase f, then that means that capital G of x and capital F of x capital G of x equals to capital F of x plus c, where c is just a constant. And this might look familiar to you from studying translations back in pre-calculus. That plus c refers to a vertical shift. So geometrically, the graphs of capital G of x and capital F of x are actually the same shape. They just have a vertical distance between any two corresponding points on their graphs that's equal to c. So for example, if we had, let's say, three different functions, so how about p of x equals to 3x squared, q of x equals to 3x squared plus 5, and let's say capital R of x equals to 3x squared minus 100. And if we find the derivative of each of those functions, so p prime, q prime of x would be 6x, and r prime of x would also be 6x. So all three of those functions have the same derivative, right? We can say p prime equals to q prime, which also equals to r prime, which means that p of x, q of x, and r of x are antiderivatives of the function, I'll call it lowercase f of x equals to 6x. And they're antiderivatives of the function 6x because all of their derivatives are equal to 6x. And then if you're looking closer at their equations, q of x is just the graph of 3x squared, so the graph of p of x shifted up 5 units, and then r of x is the graph of p of x shifted down 100 units. And so that constant, since the derivative of a constant is equal to 0, it doesn't change the derivative. of any of the functions, but it just is a shift. All of them are parabolas with the same exact shape. They're just shifted vertically up or vertically down. So let's look at this next example. So we want to show that both capital F of x and capital G of x are antiderivatives of lowercase f of x. So to do that, we're going to take the derivative of capital F of x and capital G of x. So the derivative of capital F of x using power rule would be 3x squared plus 4x, and then the derivative of capital G of x would also be 3x squared plus 4x. So because the derivative of capital F of x equals to the derivative of capital G of x, both being equal to 3x squared plus 4x, we can say that both of those functions are antiderivatives of the function 3x squared plus 2x, which I've named lowercase f of x.
That makes a nice sound, huh?
Okay, so each of those, capital F of x and capital G of x, end up being antiderivatives of lowercase f of x, but we could represent the general antiderivative. There's infinitely many antiderivatives that I could come up with for the function lowercase f of x, meaning there's infinitely many functions that if I took their derivative, I would get lowercase f of x equals 3x squared plus 2x. So the general antiderivative of that function I could represent as, I don't know, let's say capital H of x equals x cubed plus x squared plus c, where c is a real number. Or I could say where c is an element, to use shorthand, of the real numbers. So this brings us to the indefinite integral. So if capital F of x is any antiderivative of lowercase f of x, then the indefinite integral of lowercase f of x is defined as the integral of f of x with respect to x equals to capital F of x plus c. So let's break down what each part of this means. So this kind of S-shaped looking symbol here, that is known as the integral. Okay. And lowercase f of x is the integrand So we're taking the integral of lowercase f of x, the integrand, dx is referred to as the differential. Okay, capital F of x plus c is the general antiderivative of lowercase f of x. And that c is what we call the constant of integration. Okay, think in my classroom, that meme, the Salt Bay meme. Oops. Sprinkling the plus c's. Okay, so capital F of x is any antiderivative. That c is just an arbitrary constant. So that plus c allows us to represent just the general antiderivative of lowercase f of x. Because remember, you can determine, like basically by picking different values for c, you can find specific antiderivatives of the function lowercase f of x. But if we just put plus c to represent any constant, any real number, then that would capital F of x plus c would represent the general antiderivative. And the differential tells us what we're differentiating with respect to. Or sorry, not differentiate, what we're integrating with respect to. So basically like what the independent variable is. So integration. The process of finding the indefinite integral is called integration, or integrating f of x, or whatever the function name is, with respect to x. To integrate, or to find the indefinite integral of a function, we develop formulas based on reversing the differentiation formulas we already know. So here are some of the basic formulas for integration. So what this first one says is basically if you're integrating a constant, right? K is a constant. When you integrate a constant, you get K times X plus C. Don't forget the plus C, that constant of integration. Now, if you're integrating x to the r power, this is basically reversing the power rule. Or you could think of it as like power rule for integration. When we integrate x to the r power with respect to x, it's 1 over r plus 1. So basically 1 over, you add 1 to the exponent, times x to the r plus 1 power. So add 1 to the exponent again, and plus c. The integral of 1 over x with respect to x, which is this, 1 over x, remember, can also be written as x to the negative first power, is natural log of absolute value of x. And we'll talk about why it's you have to have those absolute value bars there, plus c. And then the integral of e to the x with respect to x is e to the x plus c. And that makes sense, right? Because the derivative of e to the x is just e to the x. Okay, so I just want to give you a couple examples. So when we're integrating a constant, so like let's say that we're integrating 2 with respect to x. The integral of 2 with respect to x would be 2x plus c. That's because if we were to take the derivative of 2x plus c, we would just get 2. Or if we want to integrate, 17 with respect to x, the integral would be 17x plus c. Again, the derivative of 17x plus c would just be 17. Okay, so this is the power rule for integration. Let's say we're integrating, x squared with respect to x. So 1 over 2 plus 1 times x to the 2 plus 1 power plus c, which if we simplify that, is equal to 1/2 times x to the third power, 1/3 times x to the third power plus c. Well, if we took y equals to 1/3 x cubed plus c and took the derivative, well, 3 times 1/3 is 1. Subtract 1 from the exponent would be x squared, and the derivative of c is 0. Or if we want to integrate x cubed, let's use a different variable than x. Let's do like t cubed so that we're integrating with respect to t. So my differential will be dt. And that would be 1/3 plus 1 times t to the 3 plus 1 power plus c. And you should be able to start doing some of these in your head, so not having to write out the entire rule. And you could see if you were to take the derivative of 1/4 t to the 4th plus c, you would get t cubed. Or if we were to integrate, let's say just x to the 1st power with respect to x, that would be 1/, that's a power of 1, so 1 plus 1, times x to the 1 plus 1 power plus c, which simplifies to be 1/2 x squared plus c. Okay, the integral of 1/x with respect to x ends up being the natural log of absolute value of x plus c, and it's important to put that absolute value. Let's say we had a function ln of x. The domain of ln of x is x strictly greater than 0, which means that when we take the derivative, we get 1/x, and that's for x strictly greater than 0, so for the same domain. If we had, let's say, capital G of x equals to ln of negative x, where the domain for capital G of x would be x strictly less than 0, well, then when we take the derivative, thinking chain rule, that would be 1/-x times -1, which is 1/x, but for x greater than 0. So notice that we end up with the same derivative for each of those functions. So since the domain, the implicit domain of the function 1/x is all real numbers except for x equal to 0, when we integrate 1/x, so when we find the general antiderivative of 1/x, we make it the natural log of the absolute value of x so that their domains match. Okay, so now both of these functions will have a domain of x strictly greater than 0 or x strictly less than 0. All real numbers except when x is equal to 0. And the integral of e to the x is e to the x plus c. That's because the derivative of e to the x is just e to the x. So similar to how we had a constant multiple rule for differentiation, anytime you have a function that you could think of as being multiplied by a constant, you can technically pull that constant out. So for example, if we wanted to integrate like 6x with respect to x, you could think about pulling the 6 out and then integrating x with respect to x. So when we integrate x with respect to x, power rule for integration, that would be 1/2 x squared. And then don't forget your plus c. And then you can just multiply that 6 back in. You don't have to pull out, like when you're showing your work, you don't have to pull the constant out, but you're thinking about the constant still being there, multiplying it in. Okay, and then just like we had sum and difference rules for differentiation, we also have sum and difference rules for integration. So let's say that we're integrating a polynomial function like 3x squared plus 2x minus 7. We could think about integrating each term with respect to x. So that integral can be rewritten like that, where then we just think about integrating each piece. And I could also think about pulling the constants out. This step does not need to be shown, but if you want to write it down at least in the beginning, that's fine. Okay, so it would be 3 times 1/3 x cubed, and then plus 2 times 1/2 x squared minus 7x, and then don't forget your plus c. You have to have the plus c. Then we simplify and get x cubed plus x squared minus 7x plus c. So that would be the general antiderivative of 3x squared plus 2x minus 7. Okay, so let's work through a few examples now that we've gone over some of the basic rules. So here we could pull out the 2. And we're using power rule for integration. So I'm going to add 1, or I'm going to take the exponent and add 1 to it. And don't forget your plus c. So that ends up being 2 times 1/8 times x to the 8th power plus c, or 1/4 times x to the 8th plus c. And you can always check that you've integrated correctly by taking the derivative of your antiderivative. So if we took the derivative of 1/4 x to the 8th plus c, right, we would get 2x to the 7th plus 0. So it works. Okay, I'm not going to split this up into sum and difference of different integrals. I'm just going to think about integrating each term, which I'm allowed to do because of that rule. So I'll have, when I integrate x to the 4th, I'll get 1/5 x to the 5th. I'll have the 3 there, and then when I integrate the x, that's going to be 1/2 x squared, and then minus 9x plus c, and then just simplifying a little bit. Okay, we're integrating another polynomial. Again, if you want to split this up into a sum and difference of polynomials, and what I mean by that, if we wanted to write this as the integral of 3x to the 5th dx plus the integral of 2x to the 4th dx minus the integral of 6x squared dx plus the integral 8 dx, you could. And then for each integral here, you can pull out the constant. And you only need the plus c at the very end. So you don't need to put a plus c for each of these integrals, just at the very end. So when we integrate the x to the fifth, that would be 1 over, we add 1 to the exponent, so 6 times x to the sixth. And when we integrate x to the fourth, that's 1/5 times x to the fifth power. And when we integrate x squared, that's 1/3 times x cubed. Integrating 8 is 8x. And don't forget your plus c. And then you can just simplify. Okay, I can pull out a 4 when I integrate 4 over x. Okay, so the integral of 1 over x, remember, is natural log of absolute value of x. And that'll end up being times 4. Don't forget your plus c. And then sometimes, just like whenever we use power rule for derivatives, it can be helpful to rewrite the function that you're integrating so that you can apply that reverse power rule. So like I can rewrite 2 over the square root of x as 2 times x to the negative 1/2. So then I can pull the 2 out. And applying power rule, that would be 1 over negative 1/2 plus 1, which is the same as adding 2 over 2, times x to the negative 1/2 plus 1 power plus c. So that ends up being 2 times 1 over 1/2 times x to the 1/2 power plus c. 1 divided by 1/2 is 2, and then 2 times 2 is 4. So that simplifies to be 4x to the 1/2 plus c. Okay. And here I'm just going to integrate term by term. I can use power rule to integrate x to the 2/3. So it's 1 over 2/3 plus 1, and I'm going to write 1 as 3 over 3. Times x to the 2/3 plus 1. Again, going to write 1 as 3 over 3. When we integrate e to the x, we just get e to the x. And when we integrate 4, we get 4x plus c. Okay. So 2/3 plus 3/3 is 5/3. 1 divided by 5/3 would be 3/5. And then just plus e to the x plus 4x plus c. Now there is no quotient rule or product rule for integrating. So this quotient, at least for now, until we develop some other strategies, I need to rewrite this function as a sum or difference of terms. So basically I cannot integrate the way that the function is written right now. So I'm going to rewrite this as t cubed over t squared. I'm going to split up the fraction. Plus t over t squared plus 1 over t. And then simplifying that, t cubed divided by t squared is t. T over t squared is 1 over t. And then 1 over, oh, that's 1 over t squared. I'm going to rewrite that as t to the negative second power. I'm going to leave 1 over t as 1 over t because I know what the integral of that is. Integrating each piece, when I integrate t with respect to t, that's going to be 1/2 t squared. The integral of 1 over t will be natural log of absolute value t. And then plus, I'm going to write that one out, 1 over negative 2 plus 1 times t to the negative second plus 1 power plus c. And then just simplifying. That'll be minus t to the negative first power, which can also be written as 1 over t, plus c. So finding the constant of integration. So for this particular problem, we are given that f prime of x is equal to x over 1 over x, and that f of 1 is equal to 3/2. And we want to find the equation of capital F of x. Basically, this is a point that lies on the graph of capital F of x. We're given the derivative of capital F of x. So we're going to find the general antiderivative of x minus 1 over x. Okay, so when we integrate x minus 1 over x, that's 1/2 x squared minus natural log of absolute value of x plus c. This is going to represent capital F of x, but we want to find the specific antiderivative that capital F of x is, meaning we want to find the specific antiderivative that passes through this point. So we can actually plug in 3/2 for capital F of x, and then we can plug in 1 for x here, and solve for what c is. So we'll have 3/2 equals to 1/2. Natural log of 1 is this 0. And then if we subtract 1/2 from each side of the equation, well, that'll give us c is equal to 1. So capital F of x, the equation for capital F of x is going to be 1/2 x squared, not plus, minus natural log of absolute value of x plus 1. So basically, this is the antiderivative of this function that also passes